This is a TK Academy course, where the T and the K stand for Team Knowledge for architects and designers. This is a specialty course, and the topic is Security Engineering and Anti-Terrorism Force Protection Measures. These are the learning objectives for this course. After completing this course, you will be able to identify the types of aggressors and tactics employed against buildings. Identify typical assets contained within buildings that require protection. Describe how the level of protection is determined. Identify the 21 minimum standards for anti-terrorism design in new and existing buildings. We'll start this course with a bit of trivia. What was the first recorded act of terrorism conducted against the United States and American citizens? The answer? The Wall Street bombing in New York City in 1920. At noon on September 16, 1920, a horse-drawn buggy loaded with 100 pounds of dynamite and 500 pounds of cast iron slugs exploded across the street from the J.P. Morgan Bank headquarters in downtown Manhattan, New York. The explosion blew out windows for blocks around, killed 30 people immediately, injured hundreds of others, and destroyed the interior of the Morgan building. Those responsible were never found, but evidence suggests that the act was conducted by anarchists. Those who perform hostile acts against assets such as equipment, personnel, and operations are known as aggressors. Aggressors fall into 4 different categories. They are criminals, protesters, terrorists, and subversives. The objectives of aggressors can include inflicting injury and death to people, destroying or damaging facilities, property, equipment, or resources, stealing equipment, materials, or information, or creating adverse publicity. Aggressor tactics can vary greatly, but they generally fall in one of these categories, which are listed from the most catastrophic to the least severe. They include vehicle bombs, exterior attacks, standoff weapons and ballistics, forced entry, covert entry, surveillance and eavesdropping, mail supply bombs, airborne and waterborne contamination. The vehicle bomb tactic is usually considered the most catastrophic. This is when an aggressor attacks an asset using a vehicle that is laden full of explosives or explosive material. Vehicle bomb threats are considered either moving or stationary. Past examples of vehicle bomb tactics used against the United States are the U.S. Marine barracks attack in Beirut, Lebanon in 1983, where an aggressor drove a vehicle through the gates and crashed into the barracks, setting off an explosion and destroying the building. The Murrah Federal Building in Oklahoma City in 1995, where a vehicle laden with explosives was parked adjacent to the building when the explosives were detonated, destroying most of the building. And the 9/11 coordinated attacks in New York City and Washington, D.C. in 2001, where aerial vehicles were flown into buildings, destroying both the World Trade Center towers and severely damaging the Pentagon building. An exterior attack tactic is an attack against the exterior of the building. The aggressor attacks the asset using physical force, weapons, or explosives. Weapons can include things such as throwing rocks, swinging clubs, setting off grenades or improvised explosive devices, or even setting the building on fire. The standoff weapons and ballistics tactic is when an aggressor fires weapons at an asset from a protected distance. To do so, the aggressor requires a clear line of sight or clear line of flight from the aggressor's position to the target. These type of attacks are difficult to detect. Examples would be small armed ammunition, such as from pistols, rifles, or automatic weapons, mortars which are launched at an asset, or rocket-propelled explosives. A forced entry tactic is when an aggressor has the primary goal of gaining access to an area. Aggressors gain access to the facilities using tools or explosives to breach building components or other barriers such as fences and gates. The basic defense strategy is to detect an early attempt and to delay the aggressor long enough for a response force to be able to intercept and intercede. A covert entry or insider compromise tactic is when an aggressor attempts to enter an area or facility using false credentials or an authorized personnel attempt to compromise the internal security for the benefit of an aggressor. This tactic is extremely difficult to detect. Surveillance and eavesdropping occurs when an aggressor remains outside of a controlled area and attempts to gather information from within. This is done by visual surveillance, acoustical eavesdropping, or electronic emanation eavesdropping by means of electronic devices or wiretaps. When an aggressor places explosives or hazardous material and packages to be delivered to a facility, this is considered a mail or supply bomb tactic. The objective or the target is assumed to be located at the facility that is receiving these packages. These are typically smaller devices that can fit into a small box or envelope, or hazardous materials such as resin, which can be placed into an envelope and sent through the mail. The final aggressor tactic category is airborne and waterborne contamination. This occurs when an aggressor introduces contaminants, such as toxins and poisons, into the air intake or the water supply to a facility. This is very difficult to detect, and the best protection is prevention. Protection is provided by establishing toxic-free zones into which all incoming air and water is filtered, but this is a very costly method to implement. Airborne and waterborne contamination would be considered a biological attack. An interesting statistic is the relative cost to produce biological weapons compared to conventional weapons and other weapons of mass casualties. Conventional weapons are the costliest to produce, with a rough cost of about $2,000 for a square kilometer of casualties. But biological weapons are extremely cost-effective compared to other weapons, costing only about $1 for every square kilometer of casualties affected. Consideration of the aggressors that may be present, plus the tactics that may be used, and the tools and weapons that are available, we determine what the threat is to our assets and facility. We have been discussing the need to protect assets from aggressors and aggressors' tactics. Assets can be categorized into primary assets and secondary assets. There are different types of assets, although personnel is probably the number one asset for the protection of human life. Other assets may include vehicles or equipment, arms, ammunition, and explosives, AA&E, medical supplies, communication equipment, water and food, and information. All assets have value. Some assets are more valuable than others. The asset's value is determined by assessing the asset's importance or criticality to the user's needs or operations, the ability to replace that asset if it is lost or compromised, and the relative or monetary value of that asset. When an asset's value is being evaluated, it is given a rating factor on a scale of 0 to 5, with 0 being the lowest or negligible impact, up to 5 being a catastrophic impact if that asset is compromised. The likelihood of aggression against the asset is also evaluated. It is determined by assessing the asset's characteristics, such as its profile and visibility, the asset's usefulness, the availability of other such assets, past incidents against such assets, a history of local incidents, accessibility to the asset, the effectiveness of local law enforcement, and deterrence that is present. The likelihood of aggression is also given a rating on a scale of 0 to 5, 0 being a low likely occurrence, to 5 being a high probability of aggression. The asset's value evaluation factor times the likelihood of aggression factor is what we use to determine the level of protection. This falls within a scale of 0 to 5, having very low level of protection, up to the highest category of 20 to 25, being a very high level of protection required. Time for a bit more trivia. The question: what act of terrorism led to the development of anti-terrorism force protection measures in federal buildings? A. The Centennial Olympic Park bombing in Atlanta, Georgia, 1996. B. The Khobar Tower bombings in Dhahran, Saudi Arabia, 1996. C. The Murrah Federal Building bombing in Oklahoma City in 1995. D. The World Trade Center bombing in New York City, 1993. E. The U.S. Marine Barracks bombing in Beirut, Lebanon in 1983. F. The September 11th coordinated attacks on the U.S. in 2001. Or G. The Boston Marathon bombing in Boston, Massachusetts, 2013. The answer? C. The Murrah Federal Building bombing in Oklahoma City in 1995. After that event, the government developed anti-terrorism force protection measures to protect federal buildings from terrorist attacks. The Department of Defense led the way in developing anti-terrorism force protection minimum standards for both new and existing buildings. Currently, there are 21 required standards. There are also 17 recommended standards. The standards are multidisciplined and can be categorized into site planning, structural design, architectural design, and mechanical electrical design. The degree to which anti-terrorism force protection measures are applied depends upon the building type. There are currently 3 different building classifications. The first is billeting, which is any building or portion of a building in which 11 or more personnel are routinely housed. These are commonly barracks or dormitory buildings. Second is primary gathering buildings, which is a building routinely occupied by 50 or more personnel. Most buildings will fall in this category. The third is inhabited buildings, which is a building or portion of a building routinely occupied by 11 or more personnel with a population density of greater than 1 person per 430 gross square feet. These would commonly be warehouse or storage facilities. The first standard is to maintain minimum standoff distances. This is to protect a building or an asset away from a vehicle threat. The best way to defend is to maintain a safe distance between the threat and the asset. Minimum distances away from buildings shall be maintained according to the building category. When the minimum standoff distance can be met, conventional construction may be used. When minimum distances are not available due to limitations of the site, building hardening will be required and designed accordingly by conducting a blast analysis for the achievable distance and the appropriate level of protection. This applies to parking, roadways, new buildings, existing buildings, and trash containers. There are multiple factors that go into determining the minimum standoff distance required for both new and existing buildings. The first being whether it is located within a controlled perimeter, such as being located on a military installation. The next being what the building category is, as defined earlier as either billeting, primary gathering building, or inhabited building. The level of protection is established for defending and protecting the asset. Then the building structural system is determined as utilizing load-bearing walls at the exterior or non-load-bearing walls. Finally, this gets into the conventional construction technique of the building envelope and the materials and systems that are used at the exterior wall. This identifies the minimum standoff distance as required, but there is also a minimum if the building is constructed of materials that are not already identified within the conventional construction standoff table. For facilities that are located within a controlled perimeter, the minimum standoff distances have been eased from earlier versions of the standard. However, parking and roads must still be outside the minimum standoff distance requirements. For facilities that are constructed outside of a controlled perimeter, the standoff distances are much greater to keep vehicle threats away from the occupied buildings. The second minimum required standard is titled Unobstructed Space. An unobstructed space is a zone around the perimeter of a building where there is no concealment from observation of an explosive device 6 inches or greater in size. For buildings that are built within a controlled perimeter, the unobstructed zone extends to the same distance as the standoff. Plantings within an unobstructed space are allowed only if plantings cannot provide an opportunity to conceal an explosive device. Mechanical and electrical equipment cannot be placed within any unobstructed space if it can be used to conceal an explosive device. If a screen wall located within an unobstructed space is more than just a single wall, it must be enclosed on all 4 sides and on top. Standard 3 addresses vehicle drive-up and drop-off areas. Facilities that require vehicle access into the standoff zone, such as for loading docks, shall be permitted only if driving areas are clearly marked and vehicles are not allowed to be unattended. Standard 4 pertains to access roads. Where access roads are necessary for the operation of the building, ensure that access control measures are implemented to prohibit unauthorized vehicles from using those access roads within the applicable standoff distance. This also pertains to access for emergency vehicles. The restriction of unauthorized vehicles can be accomplished with cable gates or signage stating authorized vehicles only. Standard 5 pertains to parking beneath buildings or on rooftops. This is not permitted. You may not have a building that has parking below an inhabited portion of the building or located on the roof. Standard 6 requires design for progressive collapse avoidance. Structural design must resist progressive collapse and shall be required on all DoD buildings that are 3 stories and higher. Basements are considered a story if they have 1 or more exposed walls. There are 2 methods used for designing for progressive collapse avoidance. The first and simplest method is the tie force method. This resists progressive collapse through the structural redundancy that ties members together to bridge over damaged areas. This is permitted for use in very low and low levels of protection only. The second method is the alternate path method. The alternate path method resists progressive collapse by modeling the structure's capacity to bridge over missing or deficient components. The idea behind this is that if a building has a column that is blown out or destroyed along the exterior wall, the rest of the building will not collapse. The tie force method for progressive collapse avoidance includes several rules of reinforcing steel bars that are placed in continuous bands around the floor slab perimeter to form a horizontal spandrel. These bands must be wrapped around openings within the slab without any interruptions. The splices in the bars are formed using mechanical couplings or overlapping bars. The spaces between the splices must be staggered at a minimum of 24 inches. After the continuous horizontal spandrel has been placed around the perimeter of the slab, reinforcing bars will be placed continuous from one horizontal spandrel to the opposite end of the slab with hooks on each end that will wrap the farthestmost band of the spandrel. Bars must be continuous and uninterrupted by any slab penetration or opening. Smaller aggregate and concrete should be used to achieve the flow necessary between the slab reinforcing. It is also recommended to use a 5-inch concrete slab to account for all the additional reinforcing that must be placed within it. Standard 7 requires structural isolation. This applies to building additions that must be structurally independent from the existing building. This minimizes the possibility of collapse of one part of the building that would affect the stability of the remainder of the building. Where areas of a building do not meet the criteria for classification as an inhabited building, the structure should be designed to be independent from the adjacent inhabited areas. Standard 8 addresses building overhangs. Building overhangs that have an inhabited space above them, where an individual could gain access to an area underneath the overhanging area, shall not be permitted. This does not pertain to uninhabited areas such as a roof overhang or a canopy. Standard 9 for exterior masonry walls requires that unreinforced masonry walls are prohibited for the exterior wall of a building. All exterior masonry walls must be reinforced. Standard 10 relates to windows and skylights. There has been a great amount of emphasis on this standard over the years, and for good cause, being that windows make up the weakest part of the exterior wall plane of any given building. A recent change to the standard is that much of the blast resistance of the glazing is no longer required if the facility is located within a controlled perimeter. When the minimum standoff distances are being met and the facility is using conventional construction, the glazing must be a 1/4-inch laminated glass for very low and low levels of protection. For higher levels of protection, the glass thickness must be determined by ASTM F2248, which is the standard practice for specifying an equivalent 3-second duration design load for blast-resistant glazing fabricated with laminated glass, and ASTM E1300, which is the standard practice for determining load resistance of glass and buildings. Typically, on low or very low levels of protection, the 1/4 inch laminated glass will be sufficient. When it is an insulated glass unit, the laminated glass must be located on the inboard panel. The window frames must be fabricated of either aluminum or steel. Wooden or vinyl windows are not allowed. If the project is required to meet blast mitigation ratings, the frame members shall resist the deflection of the glass at the edges supporting the glazing. Glazing units are to be installed with frames using structural sealant on the inboard side of the window. The entire premise for blast mitigation at windows is to be able to keep the window and the glass from becoming dislodged and thrown inward into the inhabited portion of the building. This relies heavily upon the connections which attach the window frame to the adjacent substrate to be able to transfer those blast loads to the building structural system. The connection design load shall be determined according to ASTM F2248 based upon applicable explosive weight at the standoff distance. The design of this connection must be proven by either calculation or by demonstration. Additionally, the allowable fastener loads will be recommended by the fastener manufacturer for the materials to which the window is being connected. The blast loads shall be distributed to the structural elements supporting the window from the tributary area with the design load of 8 times the glazing resistance. Units are analyzed in one of two ways in how they transfer blast loads to the building window frame and the adjacent wall structure. The window glazing panel may be analyzed as a one-way deflection where the anchors are at the top and the bottom and the glass deflects in just one direction. Or the glass unit may be evaluated as a two-way deflection in which the blast loads are transferred to all 4 adjacent sides of the window frame. The blast load at the window must be transferred into the building structure. In a frame solution, steel blast frames are fabricated at the size of the window rough opening. The blast frames are attached to the building structure. This creates a rough opening for which the window frames are installed and attached to transfer the loads into the building structure. If there is a curtain wall system, it is typically backed by a steel frame that reinforces the aluminum framing deflection. Windows that are connected to the blast frames in either a punched opening or curtain wall system transfer the loads of the blast from the window frame into the building structure. A similar approach applies to precast or concrete walls. However, instead of the window rough openings being framed, they are cast as openings in the precast or concrete wall panels. The window frames are installed in rough openings and anchored directly into the precast or concrete panels. The precast and concrete panels serve as the blast frames, absorbing the blast load and transferring the loads from the windows into the wall, which is the building structural system. When concrete or precast walls are being used, the internal steel reinforcement within the wall panel needs to be held back from the rough opening face by not less than 2 inches to allow adequate room for the frame anchors to embed into the concrete. Blast-resistive windows and glazing systems can be very costly. When utilized within certain limitations, the cost of blast-resistive windows can be comparative to that of conventional windows and glazing systems. When used in large expanses of the wall or used in non-conventional means, blast mitigation glazing costs can be significant. There are general rules of thumb for the design of blast-resistive windows to keep costs from escalating. Use punched windows or ribbon windows and avoid the use of curtain walls. Provide for direct attachment to the structure at the sills and the heads. Provide window opening sizes of 32 square feet or less. Provide individual window panels of 10.8 square feet or less. Design the height and width proportions of a window as equal as possible. Standard 11 applies to building entrance layout. It states that when a main entrance of a building faces an installation perimeter, people entering and exiting the building are vulnerable to being fired upon from vantage points outside the installation perimeter. To mitigate those vulnerabilities, the design should ensure that the main entrance of the building does not face an installation perimeter or other uncontrolled vantage points that have direct lines of sight to the entrance. Standard 12 for exterior doors states that all exterior doors shall open outward so that the doors will seat into the frame in response to an explosive blast, and they are not thrust into the building as hazardous debris. In most cases, exterior doors will swing outward for egress requirements, and this is typically not an exception to the standard building norm. Standard 13 looks to mitigate the threats of an explosive or hazardous material being delivered through the mail system. Mailrooms are to be located at the exterior perimeter of a building and should have their own dedicated building entrance. They should be located as far from heavily populated areas of the building and critical infrastructure as possible. Mailrooms are to be sealed off from the rest of the building and have their own envelope system. Standard 14 addresses roof access. Its goal is to eliminate all external access to the roof and provide roof access only from internal stairs and ladders. Standard 15 is titled Overhead Mounted Architectural Features. Overhead mounted architectural features weighing 31 pounds or more shall be mounted to resist the force of 1/2 times the component weight in any direction and 1.5 times the component weight in a downward direction. Standard 16 addresses air intake. It states that air intake for HVAC systems shall be mounted not less than 10 feet above the finished grade at the building exterior. This is to mitigate the threat of someone placing a toxic or poisonous substance outside the air intake that gets pulled into the air distribution system and spread throughout the building. Standard 17 again addresses the threat delivered through the mail system. This standard specifically addresses mailroom ventilation. It states that for heating and cooling systems, the airflow systems to the mailroom must remain separate from the main building system. There must be a dedicated exhaust system to maintain negative air pressure from the remainder of the building. Mailroom ventilation must have outdoor air intakes, air relief and exhaust with low leakage isolation dampers that shut automatically to isolate the mailroom. And the mailroom should have separate controls to isolate the mailroom in the event of a suspected or actual chemical, biological, or radiological release. Standard 18 requires an emergency air distribution shutoff. This is for a situation in which a poisonous or toxic substance has been delivered to the building. The shutoff is a way to mitigate that from being circulated throughout the entire facility. An HVAC control system shall include the emergency shutoff switch that can immediately shut down the air distribution system throughout the entire building. The shutoff switch should be easily accessible to the building occupants, and the shutoff switch should automatically close all outdoor intakes, relief air, and exhaust openings. Standard 19 pertains to equipment bracing. This is in similar vein as the earlier Standard 15 for architectural features. It states that overhead utilities and equipment weighing 31 pounds or more shall be mounted to resist the force of 1/2 the times of the component weight in any direction and 1.5 times the component weight in the downward direction. This is typically achieved by using seismic braces and supports. Standard 20 is to restrict access underneath a building. It states that access to crawl spaces, utility tunnels, and other means of under-building access shall be controlled. This means it is allowed, but it must have a locking device or alarm to prevent unauthorized access. The best means of compliance is to design a building with no crawl spaces or tunnels. Standard 21 is for mass notification. All buildings must have the capability to provide real-time information to building occupants during emergency situations. This information relayed must be specific enough to determine the appropriate response actions, and legible enough that the message can be clearly understood. Mass notification systems are typically integrated into the fire alarm systems within a building. This brings us to the conclusion of the specialty course on security engineering and anti-terrorism force protection measures. If you enjoyed this course, please give it a thumbs up and leave us a comment. Also, be sure to subscribe to our YouTube channel for additional courses and content from TK Architecture.